Hello and welcome to the fifth lesson. And today we're looking at introduction to magnetism. So we're moving away from electricity for a lesson or two, and we're going to look at magnetism. So today I just want you to be able to explain basic magnetic phenomena as you see them in the real world, and I got some hands-on activities for you to try after. All right, so what do we know about magnets? Magnets, there are naturally occurring magnets in the Earth, and it's called lodestone. So that is a type of material that is naturally magnetic. They were first discovered, bit of a true story. Shepherds, when they were in the mountains or in the hills watching their flocks back in the old days, they had these staffs called crooks, which helped them herd the sheep. And when they sat all day, those crooks were made out of metal, and they were in contact with the lodestone. Those crooks became magnetic, and it's kind of the first folklore on how the lodestone was located or identified. So, kind of neat. Magnetic fields. So we talked about electric fields earlier, and just to review, electric fields, if you have a positively charged particle, the magnetic field or the electric field, kind of pushing things away. So they work very, very similar to electric fields. And the force of attraction, repulsion, is caused by dipoles. So we're not going to have positive and negative anymore. We're going to have north and south on a magnet. All right. So we're not dealing with positive and negative in this case. So what are two defining characteristics? Magnetic fields occur naturally in substances that have magnetic character, and that's due to their makeup inside. Okay, so magnetic fields, they occur everywhere in the world around us. You right now are probably are sitting in a magnetic field, and we'll talk about that in a minute. And what happens is if we bring one magnet in the area of another magnet, it can affect the magnetic field, similar to electric. But also, in the next lesson or two, we're going to talk about the connection that it affects electric charges, and there's a connection between magnetism and electricity, which is kind of neat and has allowed for a lot of inventions to occur. So magnetic character. So magnetic character, it's related, the topic here, related to the condition of the atoms, and it's not fully understood. So why is there magnetic fields? Well, we don't completely understand, so that's why we have something called domain theory. Okay, domain theory, because at this point in time it's exactly that. This is what we're guessing is happening. So domain theory is that all large magnets are made up of little regions called domains. Okay, these magnetic characters of the domains are have the presence of dipoles. So they're basically, magnetic material is made up of a whole bunch of little magnets inside. And it's those dipoles, which is the north and south, that interact. So, you're not gonna regurgitate the definition for me if I ask you, and I will. Domain theory will be on the quiz, test, exam, assessment, because it is important. You're not going to regurgitate or write this out for me. You're going to give me a diagram. All right, keep it simple. So if we have material, non-magnetic, so that's where we'll start. Non-magnetic, so looking inside, what you have is a whole bunch of little magnets that are randomly placed throughout. All right, they look like that. I drew my thing way too big because I don't want to draw that many magnets. So I'm going to cheat and we'll shorten this up a little bit here. So, whoops. Okay, so that's what non-magnetic material looks like in theory. That's what we're hypothesizing. And they have a whole bunch of positive and negatives. All right, so we'll just kind of randomly put them in. Positive and negatives. So this is non-magnetic material. Okay? So what's the difference between it and magnetic? Well, this is what we theorize. When something becomes magnetic, we are theorizing that those dipoles, or those domains inside, the dipoles of those domains align. So then all of a sudden those rectangulars, or those little magnets inside the material, all of a sudden align. So you get this. So So the domains then rearrange themselves, and the dipoles align like this. And I'm doing positives and negatives. This should be norths and souths. Isn't that just peachy keen? North, south, north, south, north, south, north, south. Probably wondering, why did he say we're not using positive and negatives, and now he's using them? Anyway, I apologize. But you get the general idea. This is domain theory. This is how we theorize or believe materials become magnetic. So those dipoles align, or force the domains to align, and when they become nice and aligned in a matrix like that, they become magnetic. All right, so that's your domain theory. So rather than putting this on some form of cheat sheet or trying to memorize it, simply use the diagram and just explain to me in point form, domains align, and that's it, basically. It causes material to be magnetic or become magnetic. All right. Remember, always start with the diagram when you're trying to explain something. It makes it a lot easier in the write-up. All right. Moving along. Materials that allow for dipoles to align create a greater magnetic character. There's some materials that align much easier. So your nickel, your iron, your cobalt. Most of you, probably in grade 3, created a magnet with the nail, wrapped the nail around, put a battery on overnight. Material became magnetic. All right. So metals generally become magnetic a lot easier, and certain metals obviously become more easily become magnetic. All right. Law of magnetic forces. This is going to look pretty similar because it's very similar to the electric. Similar magnetic poles repel each other. So north, north. So you remember I did this with positives the other day. They're going to repel each other. However, if I have a north, south, south, north, there is a force of attraction between them, pulling each other closer together. And that's the second part, dissimilar poles attract. So very, very similar to our electric theory. Magnetic phenomenon. So there's a couple things here, definitions of terms. Magnetic induction. That means that this is a process in which we make metals ferromagnetic. This is just a fancy word for metals that can be magnetized. All right. Permanent and temporary magnetism. Okay. Lodestone is a permanently magnetic material. Okay. Temporary magnetism is like the nail that you may have done in I think it's grade 3, they do that in the science for magnetic forces. You can magnetize a nail short term. It doesn't stay magnetic forever. All right. So the domains don't want to stay in that arranged formation. Reverse magnetization, so that means that we can switch a magnet's polarity. So we can make a magnet that has a polarity of north-south. We can force it to then become south-north, so we can reverse its polarity with a stronger magnet. If you drop a large magnet, or drop any magnet, and breaks into smaller pieces, the smaller pieces become little components of the magnet. All right, so the large piece becomes a couple broken pieces. I'm upset and yelling at you because you broke my magnet. But in the end, we end up with north-south. All these little components become magnets with the same properties as the larger one. And maximum strength. There is a limit to how strong a magnet can be. It depends on the material. And when we get into electromagnets, it depends on the current. We'll talk about that a little bit later. Finally, sketching magnetic fields. It's a little bit different. The number of lines drawn are proportional to the strength of the field. So what does that mean? Well, I'm going to give you a picture. And the direction of field is defined by direction north pole to south pole is basically what that said. So looking at your diagram, I've created a weak and strong magnet. So the field lines inside a magnet run parallel. So the weak one, I'm going to put 3 parallel lines inside. And I don't know why I made these so big. All right, so there is my field lines inside a magnet. This is the weak one. So the direction inside the magnet, and be careful here, inside the magnet, the direction of my field lines is south to north. Outside the magnet, it goes north to south. So it will reconnect, and the magnetic field is now heading in that direction. That middle line I drew, I'm going to split it, all right, so that it connects back, just to make the diagram nice and symmetrical. So this is how I would draw a weak magnet, all right? Use about 3 lines in the middle. A strong magnet, I'm going to put, let's try for 5 here. 1, 2, 3, they're supposed to be parallel lines. 4, 5. So the field lines are tighter together. So field lines closer together, in a strong magnet, or that's how we represent it, magnet. All right, so I'm going to tighten these lines up, keep them closer together to indicate the strength of the magnet. I'll go the other direction, and split that middle line off. So again, moving south to north inside, north to south outside. And there is your difference between how you represent a weak magnet and a strong magnet. Okay? So those lines are much more compressed in a strong magnet. There we go. That summarizes or takes care of our introduction to magnetism. Anyway, if you have any questions in class, just ask, and then, like I said, I have some activities for you to try, so you can actually see these field lines in action. So, all right, good luck. See you tomorrow.